Hello, everyone, and welcome to another wonderful day of physical chemistry. So, today we're going to be taking a look at our electronic transitions and trying to broaden out to take a look at what these look like on more of a polyatomic level. And it turns out that most of the times when we're trying to treat molecular electronic transitions, we tend to actually work on it by focusing in on smaller subportions. So most of the time, what we're going to do is we're going to look at particular chromophores. So these are going to be parts of a polyatomic species that tend to best absorb light. So a lot of these times we're going to be looking on specific functional groups, and we're going to be taking a look at some of the more classic functional groups, what MO transitions they have, and kind of where we'd expect them to occur. So one classic example of this is a good old fashioned carbonyl. So carbonyls typically make good chromophores in essentially kind of that near UV region. So this is kind of UVB region. It is worth noting that it isn't too surprising that this can be damaging radiation, as uh, your body has lots of carbonyls in it. And a carbonyl absorption event, essentially what it does is it's an N to pi star transition. So I excite an electron from a um, non-bonding or lone pair orbital on the oxygen, and I excite it onto the antibonding orbital of the carbonyl, which can have the function of slightly elongating the system and have a little bit of extra reactivity in this state. But that said, uh, the excited state typically quickly relaxes into a safe transition. But in the meantime, it does indeed absorb some light and produces some of the color, mind you, if only in the UV region. So again, really, I'm just looking at excitations of lone pairs in the pi systems. And you're going to find that pi systems make very good chromophores because they tend to be empty orbitals and fairly low lying. Now, one of the most important things you can note is that, well, this is just focusing in on the central two atoms. And it is worth noting you can quickly modify a lot of these chromophores by playing around with your choice of R group. If you're um, And the effects may not be as simple as electron withdrawing or donating because it depends largely on where you're donating or withdrawing. What we're looking for is often going to be functional if we want to bring this uh, wavelength into the visible light. We're either going to have to destabilize our lone pair oxygens, electron donating, or have some sort of electron withdrawing character that lowers the energy of our antibonding orbitals. And this can be quite a lot more non-intuitive than a lot of organic processes. However, there is a related chromophore that we tend to see a little bit more of explicit modification of, and that's our good old friend, the alkene. So this has a little bit more of a straightforward absorption event where I go from pi to pi star. It is worth noting that this excitation occurs at about 170 nanometers, so much lower energy than the carbonyl, and much deeper in the UV vis spectra, so less likely to see it. However, it's also a little easier to see how this can be modified by R groups, as I can try and stretch out this orbital to try and lower the energy of this transition, bringing it into the visible light spectra. However, the classic way of modifying this orbital gap is our good old friend conjugation. So conjugation is one of the classic ways to modify a chromophore. And this is pretty much by making the chromophore bigger. And typically what ends up happening is I extend a conjugated pi system, is I add in an extra set of orbitals, which lowers the gap. So my lowest and highest orbital energies do go lower and higher than originally, but then two new sets that I insert in, because again, I bring in two orbitals, they have to go somewhere. These tend to be pushed a little bit closer together than I would have had from just a single pi bond. And this is actually a fairly noteworthy event. And you can see this by playing with things like Huckel theory. Longer the conjugation, narrower the gap. This is also fairly simply modified by trying to treat the system as a net particle in a box, and we're mostly looking at increasing the number of nodes. Ground state, no nodes. Uh, um, Second energy level, single node, then two nodes, then three. Increasing number of nodes, increasing number of energies, longer the box, more options. So it is worth noting that this is actually kind of a traditional way of looking at the systems. However, it turns out in terms of general organic chemistry, a lot of our chromophores do tend to be uh, in these general trends, looking at carbonyls, alkenes, and occasionally you'll bring in the occasional oxygen or nitrogen, which can join a conjugated system if it has to. However, there's a reason why inorganic chemistry has the reputation of being the most colorful of chemistry. Most of our most of the most common chromophores tend to involve metal centers, and that's because metal centers open up a whole new field of electronic excitations. So they're going to be focused. They're split into three major classes that we're going to talk a little bit more about next time. So we've got metal D to D transitions. So that's essentially where I just have electronic transitions within this metal center. Most of these are essentially going to be weakly forbidden, mostly by symmetry. However, they are still spin allowed and vibrationally just fine. We also have metal to ligand charge transfer. So this is where I move an electron from a ligand onto the pi center. And then we also have the reverse, where I take a metal to ligand, where I take an electron on the metal, move it to a pi orbital on the ligand, or the reverse, where I take a ligand electron and move it into an open orbital on the metal. Both of these actually have fairly strong intensities and often sometimes characteristic colors. Now, one of the big things worth noting is that the relationship of uh, the metal and ligand or energy levels are going to dictate which one of these we'd expect to dominate. And sometimes, because they're split into two different symmetry classes, both may occur simultaneously, just at slightly different wavelengths. So we're going to examine our metal energy levels a little bit more next time to try to get a little bit more insight into our chromophores and electronic transitions. Till next time, see you then.